Hi guys, today we're going to be learning about some of the factors affecting resistance. Now that we know a little bit about what resistance is and how it works, we can start figuring out a model to show how it works on an atomic scale and use that model to predict what will affect the resistance. Now, what causes resistance? We know that when electrons pass through an electrical component and through its resistance, the electrons lose energy, and it comes out of the resistor as heat. We also know that the resistance of the circuit component is able to slow down the electrons and decrease the rate of charge transfer, right? It can decrease the current through the circuit component if it has enough resistance. So when a metal conducts electricity, electrons move through it, right? They're the charge carriers. Now as they do so, they bump into the lattice of atoms that makes up the metal. Remember that metals, like all materials, are made out of atoms. And because the metal is a solid, the metal atoms are pretty much fixed in place, although the electrons can flow through them freely. Now, as the electrons bump into the stationary atoms, some of the electron's energy gets transferred into these atoms. Makes sense, right? We can't create or destroy energy, we can only transfer it from one place to another, or convert it into different forms. So in this case, we're transferring the kinetic energy of the electrons to the kinetic energy, or vibrational energy, of the lattice of atoms that make up the metal. A lattice is like a repeating grid. Now, the vibrational energy of atoms in a metal determines the metal's temperature, right? So the more the electrons bump into the metal lattice, and the more the atoms in that lattice vibrate, the hotter we're going to get. So when electrons flow through a metal, some of the electrical energy, that is, the movement of the electrons, is transformed into heat energy, that is, the vibrational energy of the lattice, right? So we say that the resistance of the metal has transformed the kinetic energy of the electrons into the vibrational energy of the lattice. That is, the resistance has transformed the electrical energy into heat energy. The resistance of a metal depends on a few things. It'll depend on its length and its cross-sectional area. Now, when electrons pass through a very, very long conductor, like a long extension cord, then they have more opportunities to lose energy, right? As they travel through the resistor, they can bump into more parts of the lattice. So this means that longer conductors have a higher resistance. The longer we draw out a wire, the more resistance it will have. That seems fairly straightforward, right? Now, if a material has a very large cross-sectional area, that is, if the wire is a very thick wire, then more electrons can move through it, creating a larger current. The larger the cross-sectional area, the more electrons there are in that cross-sectional area, and so the more can move through the wire. This means conductors with a large cross-sectional area, that means very thick wires, will have a lower resistance than thin wires. How does the temperature of a material affect its resistance? Well, we can see a hint in this picture over here. When the material gets very hot, the vibrational energy of its lattice of atoms, represented by the pink circles here, will increase. So we can see that these lattice atoms are jittering around very quickly in this diagram. And what this means is that if they're vibrating around more, it's easier for the electrons to bang into them, right? Because it's like they're taking up more space. So when the material gets hot, it's easier for the electrons to collide with the lattice. And what does this mean? It means that it's more resistant than if it's at a lower temperature. So as a material's temperature increases, the number of collisions between electrons and the lattice also increases. This means that the electrical resistance of the material will increase as well, right? So hotter conductors have higher resistance, although in practice it takes quite a large temperature before the resistance changes significantly. So materials which obey Ohm's law, V equals IR, are called ohmic resistors because they follow Ohm's law, right? And so the graph of the current through a material like this might look something like this. In reality though, it's very hard to find an ohmic resistor. They don't really exist. The reason for this is because the more current we push through a resistor, the higher its temperature goes. So we can't actually keep the temperature fixed if we want to measure the current through a resistor. This means that most materials aren't in fact ohmic resistors. For a small voltage, the relationship between voltage and current is linear. We can see at the start of this graph, when we have a voltage below about 2 or 3 volts, we have a pretty much linear relationship with the green line as well as the yellow line. As the current increases, which we can see on the y-axis, the temperature of the material increases. And that means that we increase the resistance of the material so that the current will lessen. Ohm's law states that we have to have a yellow line, like this one, going straight up as voltage increases. In practice, when we get up to large currents, we heat up so much that our resistance will increase. So rather than a straight line, we'll get a line that bends downwards like this. There's one other thing that can affect the resistance of material, and that's the material itself. So some materials are intrinsically better at conducting or intrinsically worse at conducting than other materials. For example, copper conducts electricity better than aluminium does. And we'll get on to one of the interesting consequences of this in a moment. The two most common conductors used in wiring are copper and aluminium, right? So remember, copper has a higher conductivity than aluminium, and aluminium has a higher resistivity and a higher resistance than copper. Now copper, because it's so conductive and it has a very, very low intrinsic resistance, is commonly used for household wiring, right? It means that we don't have to lose very much electrical energy. Aluminium is less conductive than copper. It has a higher intrinsic resistivity, but it is lighter and also in fact a bit cheaper, which makes it also used as an alternative to household wiring. So that's the end of the theory. We've learned a bit about how resistance works and what causes it, and some of the ways that we can change the resistance of a resistor. Let's go on to some questions. Question 6. If all of these wires were made of the same material, which one will have the least resistance? A short thin wire, a short thick wire, a long thin wire, or a long thick wire? So if we want to have the shortest resistance, the smallest resistance rather, then we need a very short wire. If the wire was very thin, then that would increase the resistance because we wouldn't be able to push many electrons through it. So we want a very thick wire. Our answer then is not going to be a long thin wire, but in fact a short thick wire. Thick wires have less resistance than thin wires, and short wires have less resistance than long wires. Question 7. How does the current through an ohmic resistor change as the voltage across it increases linearly? Does the current increase linearly at all times? Does the current increase linearly at first, but decrease away from the relationship as the voltage increases? Does the current increase linearly at first, but increase away from the relationship as the voltage increases? Or is it none of the above? Now, the key to answering this question is that the question says it's an ohmic resistor. An ohmic resistor always follows Ohm's law. And remember that these don't always exist in real life. Part C says the current increases linearly at first, but then increases away. This would mean that we're getting energy out of nowhere, and that for a relatively low voltage, we can have a huge amount of electric current. Part B says that the higher we try to get the current, the higher the resistance we'll get, and so will decrease away. Now this is true of resistors in the real world, but resistors in the real world are not ohmic resistors. So because we decrease away from the relationship, we're no longer following Ohm's law, which says V equals IR. So our correct answer must be A. The current increases linearly at all times. An ohmic resistor always obeys this relationship, V equals IR, which means that there's a linear relationship between current and voltage. Question 8. List 4 ways to change a metal wire so it has an less electrical resistance. Can you think of 4 ways? Well, let's start with the easy ones. We can make the wire shorter so that there's less of the wire that the electrons have to travel through. We can make the wire thicker so the electrons have more area to travel through. Now perhaps a harder one. We can cool the wire down. If we cool the wire down, then we decrease the vibrational energy of the atoms in the metal lattice. And this means that it's harder for the electrons to bump into them, which means the metal has less resistance. Now there's one more change we can make, but it won't be changing the shape of the wire. It'll be changing what the wire is made of. We can simply make the wire out of a more conductive material. Question 9. The resistance of a wire is proportional to its length and inversely proportional to its cross-sectional area. If a cylindrical wire with a resistance of 1.2 ohms is drawn out so it is exactly twice as long as when it started, how does its cross-sectional area change? So let's draw a diagram of what's happening here. We're taking a wire, which might look something like a cylinder, as the question says, and we're drawing it out so that it will have the same volume, but it will be exactly twice as long. So if this is L, then this length is 2L, right? So the cylinder becomes twice as long, but its volume stays the same because we're drawing out the wire. Now, how will its cross-sectional area, that is, the area of the circular face, change after we draw it out? Well, think back to the volume of a cylinder that you've learned in mathematics. The wire's volume, which is cross-sectional area times length, stays the same. So if we double the length, we have to halve the cross-sectional area. Fairly straightforward, right? Part B. What is its new electrical resistance? So we've doubled the length and halved the cross-sectional area. Both of these will cause the resistance of the wire to double, right? If we make the wire twice as long without changing its cross-sectional area, its new resistance will be 2.4 ohms. But if we then increase its cross-sectional area so it's only half as big, then we'll double that again. So halving the new cross-sectional area will double the resistance, and doubling the length will double its resistance again. Doubling this twice gives us 4.8 ohms of resistance. Question 10. Is a light bulb an ohmic resistor? Justify your answer. Now, what constitutes an ohmic resistor? It means that current has to increase linearly with voltage at all times. But this is not the case for a light bulb. If a resistor is an ohmic resistor, the current in the resistor increases linearly with voltage. When a light bulb is supplied with large voltages, the currents in the bulb cause its resistance to increase. And this means that the current in the light bulb will not increase linearly with voltage. It will decrease away from the linear relationship. So a light bulb is not an ohmic resistor, just like most resistors in the real world. So, that's the end of the questions. In this section, we've learned about a model of resistance and how we can use that model to predict how changes to the properties of a wire will change the resistance of that wire.